that's serving a large number of web clients, this kind of disruption may not be acceptable. Another reason is the unreliability of the software patches. The software patches can become unreliable, and this is not because the patch testers are not doing their job. It's really because that software patches are inherently difficult to test for, simply because a large number of machine configuration settings, newer versions of DLLs, and so on. So it's quite reasonable that for a particular machine configuration, the patch that's released breaks their system. And when that particular patch breaks the system, it's also hard to reverse that patch. So that's the irreversibility problem with the software patch. The reason is that you have been applying changes to our system after applying that patch, and those changes may be dependent on the patch. So undoing this patch is a non-trivial task. Lastly, because of these top three reasons, technical issues with software patches, it's not really possible to enable complete automation of the patch installation. So the user is in the loop, and oftentimes the system administrators they do a set of comprehensive testing of the patches they receive before they actually encourage their users to install the patches. So when the user is in the loop, there is an unawareness problem. The user may not be aware that their systems are vulnerable and are in need of patches. So you may wonder whether the existing firewalls are effective for the protections of these security network exploitable security hosts. The answer is not really. The existing traditional firewalls, they're typically very coarse-grained. And for example, you block a certain port when there is an incident of a large-scale worm attack. So this will incur very high false positive rate and causes severe disruption in the services. And also, the traditional firewalls are typically placed in the network, and it's a basically one-size-fits-all solution. It's trying to protect all the computers in this network. Some of the computers do not really need the protection because they have already applied the patches, and while the others do. And also, there's this lack of application awareness. Furthermore, it misses end-to-end encrypted traffic such as IPsec. So recently, there is the emergence of exploit-driven attack, exploit-driven firewalls. Basically, these firewalls try to filter according to some attack pattern using a pattern matching or regular expression. However, this kind of firewalls are vulnerable to attack code obfuscation. For example, polymorphic attacks can evade such firewalls very easily. Furthermore, the worms can spread really fast, and we all know that Slammer overtook the internet in 10 minutes, and researchers have developed newer lower bound, like within seconds, the whole internet can be overtaken. So this poses a significant challenge for exploit-driven firewalls. This requires these firewalls to do real-time signature generation and distribution. So our approach is Shield. Basically, Shields are unhost-based firewalls and using vulnerability-driven filters. Our goal is to protect the time window between vulnerability disclosure and patch application. Our approach is to characterize the vulnerability instead of various exploits. And we use the vulnerability signature for unhost-based firewall. So Shields combine the best of both of software patches and firewalls. Like patches, Shield is vulnerability specific and is independent of the variations of the attacks or exploits. But unlike patches, patches are at the code level, patching the executables, making deployment and testing very complicated. And Shield takes the advantage of the firewall being at the network level and is data-driven. However, unlike the recent exploit-driven firewalls, it's vulnerability specific, and it's not exploit specific. So the advantage of Shield is really that Shield offers as good protection as software patches, being resilient to attack variations, unlike exploit-driven firewalls. And at the same time, it's easier to test and deploy and more reliable than the software patch. So this slide shows an overview of the Shield usage. So basically, we envision that Shield will be enabled on every single desktop machine in the future, hopefully. And whenever a new vulnerability is discovered, a new Shield policy encoding this vulnerability signature is distributed to every end host. And at that time, the protection for that vulnerability is enacted. So essentially, Shield intercepts vulnerable application traffic above the transfer layer. This is actually a key advantage of Shield because Shield only needs to intercept the vulnerable application traffic. For the rest of traffic, it does not need to do anything. It does not need to do any deeper inspection. And the policy distribution is very much like the antivirus signature model. Basically, the virus signature, instead of a virus signature, we distribute a vulnerability signature to every single end host, and resulting in automatic, non-disruptive addressing, basically addressing those deployment concerns in a software patch. So this kind of distribution installation model is automatic, it's not disruptive, and it's easily reversible. So we also conducted some study over some of the security vulnerabilities in 2003 and to see whether there's a case for Shield, what vulnerabilities can be shielded. Basically, there are 49 vulnerabilities from Microsoft Security Bulletin Board, and out of these 49 vulnerabilities, 12 of them are warm exploitable. Basically, they can be, it's like a network traffic exploiting, say, a buffer overrun in the backend server. Well, all these kind of vulnerabilities, Shield can be easily, Shield can provide easy protection. Basically, Shield is very good for network exploitable security goals. Shield is endpoint based and is above the transfer layer, so we don't have to deal with IPsec encrypted traffic. You may wonder, okay, how about SSL? In that case, we would advocate building Shield on top of SSL. Nevertheless, application-specific encryption will be difficult because we don't have the access to the payload, encrypted payload. So I have just given you a nutshell on what Shield is, and next I'm going to delve into the next level of detail in the Shield design. And I'll give you analysis on our design, and I'll tell you more about our actual implementation prototype, some initial evaluations. I'll talk about related work and conclude at the end. So at the heart of shielding is really how we can model the vulnerability. So basically, the intuition behind shielding is really that the worms, like in the network traffic, there's some malicious network traffic speaking some application level protocol, exploiting some service running on your system. So all application level protocols in practice can be modeled by a finite state machine, like this one. At a particular state, you receive a message, you do something, you advance to the next state. Okay, because we're here addressing known vulnerabilities, we know exactly at which state the exploit events can happen. So now I'd like to circle this part of the state machine. This really represents the vulnerability state machine. So this really represents all the possible sequences of the network messages that can lead to the exploitation. Just to make the picture complete, within each protocol state, there's fine-grained application implementation state machine, encoding some application logic, like file being opened and stuff like that. But we're not really so concerned about that part of the logic. We're in the network, we're observing the traffic passing by, and we want to understand the precise protocol context. So we're mostly concerned about the vulnerability state machine. So what constitutes the vulnerability signature or Shield policy is really the specification of this vulnerability state machine, as well as how to recognize and react to the exploits at this vulnerable state, V4. So next I'm going to talk about the Shield architecture design. So there are three essential goals to design the Shield system. First, we need to allow enough flexibility and minimum effort to support any application level protocols. So when you have a new vulnerability discovery, you want to be able to author these vulnerability signatures fairly quickly. And secondly, we want to ensure shield fidelity. What that means is we want the shield's interpretation of the protocol context to be consistent with that of the application. Any inconsistency will open opportunities for the attackers to attack the system. Lastly, we also want to minimize and limit the amount of state maintained by shield. We don't want shield to be an alternative target of a denial of service attack. But the bar here is not very high because we only need to design shield to be as DOS resilient as the actual application. So now I'm going to talk about each goal, how we address each goal in turn. So on the flexibility aspect, basically, we use the well-known computer science principle, separate the policy from the mechanism. So the mechanism here is really the generic elements of all application-level protocols. For example, the finite state machine, and the event dispatching logic, and the session maintenance logic. And the policies really refer to the varying aspect of individual application-level protocols. For example, how do we know which application this traffic, this byte stream belongs to, and how do we identify, which event this byte stream corresponds to, as well as vulnerability state machine transitions. And we have designed a shield language to specify such policies. So now I'm going to walk you through the shield architecture. So basically, there are two data structures. On the top, it's the application specification. Basically, that encodes on encodes the policy, the shield policy. And at the bottom here is the session state. For each session, we also have a data structure maintaining the session state. So these are the modules in the shield system. Basically, when there's a new vulnerability discovered, a new policy is authored, and they're being loaded into the system as an application specification. So at the runtime, you receive a packet, and the payload of the packet first goes through the application dispatcher. Based on which executable, which process image this packet is associated with, then we decide, we know which policy to use. So then that's the policy. The policy, again, encodes, what's the state machine transitions and how to recognize the events and all that. So that's basically the guideline on how we interpret the traffic from that point on. Then the session dispatcher, based on the information like from the policy, like how can we obtain the session ID, how can we obtain the message type, and how can we understand the boundaries between the messages. Then we understand what's the event, what event this byte stream represents for which session. So then the state machine engine, based on the current state from the session state data structure, and that event, we consult the policy again. We understand which handler to invoke at that state with that event, and then we interpret the handler. And what handler does is really parses the message payload, and trying to inspect the message and to see whether an exploitation is happening. If it does, then we drop that packet or we tear down the communication session. At the end of the execution of each handler, we always set the next state for that communication session and update the session state data structure. So that was the overall system. This is overall how the system works. Now I'd like to talk about the fidelity aspect, how we ensure that the interpretation of the protocol context in shield is consistent with that the application. The infidelity will result in either the attackers evading the detection or resulting in false positives, resulting in the disruptions in the services. So there are a number of sources of inconsistencies. So basically, the protocol or message format can be misunderstood by the policy author. Well, we can address that through debugging or test, like trace-driven debugging, or using the existing protocol test suites to address that. And secondly, the event dispatching logic could be inconsistent. For example, it's wrong to use socket as a unit of dispatching. You should not, according to, here's according to this socket, I should dispatch this event to this session, because there can be multiple sessions going on for that socket, and vice versa. Similarly for the host pair. Host pair should not also be used as a unit of event dispatching. There can be many communication sessions going on between two hosts, obviously. So the key lesson we learned here is that the session is really the abstraction for event dispatching and the unit of shielding. Session is really what the state machine is modeling for. Another thing is that message can be arrived over multiple packets. It's wrong to treat a packet as a message, as this has been done in some of the intrusion detection systems. This has also been pointed out by some of the prior work. So basically, here what we need to do is that we need to do a message-based inspection rather than packet-level inspection. So on the third goal, the minimum state in shield. So basically, the session state we need to maintain is the current protocol state and the current parsing state and the handler continuation. What handler continuation is that you receive a message, and you can execute the handler as soon as you can. You receive some bytes for that message. However, you may not have received the complete message. Then the handler needs to be halted and wait for more bytes to arrive. So the handler continuation is exactly the same as the call continuation concept. So in terms of the parsing state, you may wonder, oh, gee, parsing state can be huge. There may be a huge message that you have to buffer, like rather long messages. But actually, that's not the case, because for parsing here, we're not parsing to do application logic. We're parsing here to check for the exploitations. So we only need to parse in order to do so. So we can skip a lot of fields that we don't care about. In fact, we only need to keep track of what's the current field that we're parsing. We only need to, for example, if you parse a long message, and you only need to keep track of this, maybe the last 4 bytes representing the data that you're interested in. Maybe you only need to store the partial field that you're parsing right now. So the state there is also not very much. So now I'd like to give you an example on our shield language. Shield language basically allows us to specify the protocol variations of each protocol and the vulnerability signature that uses that protocol. So here is an example for the vulnerability behind the blaster worm. So at the top is saying that it's a shield, and the first is the name of the security bulletin number for that vulnerability. It's using a TCP, and those are the ports that we're concerned about. Then in the next 2 lines, we specify how we retrieve the session IDs out of the message. For example, it's at offsite 12 for 4 bytes in the message. That represents the session ID of that message. Similarly for the message type. So that's offsite 2 with 1 byte that indicates what the message type. These information are used for session dispatching. And so then here we listed the states that are involved with the RPC protocol. And the next we specify what the events, basically. If the message type is 0B and in the incoming direction, then that's RPC bind message. So we'll further specify the protocol state machine transitions. Essentially, this is the vulnerability state machine transitions. So at a particular state, if you receive a particular event, you invoke that handler. Another important aspect is specifying the message format. For example, here we specify the message format for for the RPC bind. So this is a little bit like the struct in C, and this the keyword skip is really saying that you do not need to save any state for those fields. When you're parsing them, you only need to remember you're parsing that field, but you don't need to save the content of that field. So this is trying to minimize the state maintenance in shield. In the handler, over here, when you first, so this is the handler when you first receive a RPC bind message, and we're looking for the UUID here, and this UUID represents the RPC call that contains the
that's vulnerable, that has a buffer overrun in it. Then later on, if that RPC bind request is trying to invoke that RPC call, then we continue maintaining the session context for that session. And then when you receive the RPC request, you check for the buffer size. If the buffer size exceeds this legal limit of 1023, that means that you're being exploited. So then we tear down the communication session and return the final state for that session. So that's pretty much how the next level of detail of our shield design. So next I'd like to give you analysis on this design. So first on the scalability. So the scalability here is really how can we scale with the number of vulnerabilities. First of all, the number of shield does not grow indefinitely. We envision that after you apply shield, after you apply your patches, then the corresponding shield can be removed. Even if you don't remove that, the shield doesn't really, the scalability is still pretty good for shield because shield does application level filtering. You only filter the vulnerable applications. So if you have n vulnerabilities, n vulnerabilities in n applications, then that's pretty much equivalent to one vulnerability for each application. I'm sorry. So you have n applications, one vulnerability for each application, and this is equivalent to the overhead of one shield, basically, because of this parallelism at the application level. So then the next concern may be, okay, how about in applications like Internet Explorer or web server, there can be multiple vulnerabilities in that single application. This is also not very significant according to our study on the security bulletin of the Security Bulletin Board from 2003. Basically, we find that there's no more than 3 wormable vulnerabilities seen in any single application in 2003 for the wormable ones. So also you may worry about application throughput. Okay, here I'm giving you maybe the worst case scenario. The worst case scenario is the application throughput is at worst about halved. But actually, this would be very low impact for the customer machines. But for the server machines, you may be worried about that. But our actual evaluation shows that the impact on the application throughput is actually very small. So some analysis about the false positives. Because shield is vulnerability driven, so basically we have a near zero false positive rate by nature. However, there could be 2 sources of false positives. There could be a misunderstanding of the protocol or payload specification, as we talked about before, and this can be debugged. This can only be debugged by trace-based testing or test suite-based testing. There's also another source of maybe somewhat more contrived example of when false positives can occur. That would be for some network event, there may be a different treatment of that event based on some runtime condition, maybe based on local configuration, or maybe based on some application logic. In one scenario, it's not an exploitation. In some other scenario, it is. I think this kind of false positives will be, we should actually block those kind of traffic just to be safe. Okay, so now I'd like to tell you more about our prototype implementation. The shield prototype implementation is based on the layer service provider from Windows. What this LSP does is really intercepts the transport layer protocol, basically intercepting the send calls, receive calls, open and close socket calls, and then the shield logic is inserted in those interception to do deeper inspection. This is about like a 10,000 line of C++ code. Some of our shielding experience is quite positive. We have working shield for a number of vulnerabilities. We have the shields, working shields behind, for the vulnerabilities behind Blaster, Slammer, and Code Red, and we have more of those these days. We have done detailed study over 15 vulnerabilities and 7 protocols, and we have more of those protocols as well. This talk is slightly out of date. We also have done some throughput evaluation. Okay, so basically the shields for Blaster, Slammer, and Code Red, they have very little state. We need to maintain very little state for those vulnerabilities. Typically, it's less than 32 bytes. And also, they have very small number of states. So they incur actually very little overhead for the end-host system. So because of that, we have designed a more stressful shielding scenario. So we assume there's a server sending data to clients as fast as possible in an RPC-like fashion, in an RPC-like session over the Ethernet switch. And each session requires, each session will require 1 kilobyte of partial payload to be saved. So that will be part of the session state. So it's much more stressful than the working shields that we have, which is only 32 bytes or less. And we put an outgoing shield on the server, and what we want to see the impact on the server throughput. We used a 3.606 gigahertz CPU and 1 gigabyte of RAM for both client and server, and they're all running Windows XP. And we first use a 100 megabit per second Ethernet switch for the experiment. We can see that here, the network, the Ethernet switch is the bottleneck, and the CPU is very fast, so we can achieve pretty much the maximum bandwidth here, maximum throughput here for all clients. However, we can see some variations in the CPU usages. Like when there are less than 50 clients, the LSP, so we sort of divided up the cost and see how much LSP costs and how much shield adds to that cost. So LSP incurs rather large overhead, is about 11 to 28% of overhead, and shield only adds a little less than 3% more overhead. So after inspecting the LSP code, we realized that overhead of LSP is actually not inherent. There's some heavy copying of the socket context that caused that overhead. So that overhead can potentially be removed by very much. We also conduct the same experiment over 1 gigabit per second switch, and looking at the throughput for the server. Here, obviously, the CPU is not fast enough to keep up with the network bandwidth here. So we can see a degradation of the throughput as the number of sessions increase. So LSP degrades the throughput by about 12%, and shield degrades by 11% more. Okay. So now I'd like to talk about some of the related work to shield. So many studies have shown that the fast spreading and wide spreading nature of the worms. People have done a lot of extensive work, research in the compile time static checking, basically doing static checks for the buff overruns at the source code level. Basically, in that piece of research there's a trade-off of false negatives and false positives. There are also a number of mitigation techniques, such as DagGuard and non-executable stack or heap. But these techniques can also be circumvented by the attackers with different with new attack techniques. And also, these techniques often lead to a service denial of service attack, basically causing the system to crash. There's also, for the exploit-driven firewalls, there are new algorithms being designed to extract the attack signature in a very efficient manner. For example, early bird and autograph are all along this approach. There's also many honeypot-based approaches like HoneyD, HoneyNet, and here there's also some very extremely exciting, interesting work on Collapsor and vGround, understanding the behavior of the malware in the virtual machine environment, as well as maybe attracting all kinds of malicious traffic into one spot, into this vGround. And there's also a large body of work on network intrusion detection, such as Bro, Ron Paxson's work, and Snort, as well as traffic normalizers. Basically, in the intrusion detection system, usually it's on the edge network. There could be a discrepancy. Because you're in the network, you basically have to reconstruct the protocol context from the network layer up. So that can be very challenging because you're not exactly at the end host, and people can play various tricks to evade the detection. So then there's techniques like traffic normalizer being introduced trying to normalize the traffic so that the intrusion detection system can analyze the traffic in a more accurate fashion. So basically, I think for worm defense, for malware defense, we need all kinds of defense mechanisms playing together to be effective. And the shield, what's special about shield is that it's an unhost firewall. It does not need to reconstruct the protocol context from the network layer up. And by intercepting the transport layer and up, basic application layer traffic, we only need to deal with the application level traffic. And it's also more efficient that way. We don't need to touch the traffic that belong to the legal traffic, to the traffic that belong to, that do not have software defects in them. So there's some ongoing work in the Shield project. Our most recent work is basically going further on the generic application level product analyzer and its language design. Basically, this mechanism can be a general mechanism for not only the intrusion detection firewalling. It can also help with the network monitoring, help you analyze the protocol traffics, the application level protocol traffics, helping you maybe annotate the traffic with application level protocol semantics. I believe there are some other more interesting applications there. For example, we can also combine this kind of protocol understanding logic along with some unknown zero-day exploit detection mechanisms to potentially allow automatic signature generation, like Shield kind of signature generation. Some other ideas we have is having a Shield pod instead of, so basically we have a Shield-enabled detector basically for detecting stealthy or polymorphic attacks for the known vulnerabilities. So in the future, we believe that there will be that the stealthy worms would be much more difficult to deal with. So just to conclude, Shield is a vulnerability-specific exploit generic network filters for preventing exploits against known vulnerabilities. And we use generic protocol analyzer as a key mechanism. And we use a session and message-based inspection rather than packet-level inspection. We use a CIF description language to specify the policies. And our initial prototyping and evaluation results are quite encouraging. Thank you very much. I believe I'm quite early.
We have time for
a lot of questions. Yes.
Can you give an example of the vulnerabilities Shield is targeting other than the buffer overflow attack?
Yeah, that's a very good question. So basically, here you can think of our mechanism here is to understand the protocol context. With that knowledge, you can do a lot of things. Sometimes, for example, your protocol may have some logical errors. For example, it doesn't have authentication stage. Presumably, you can insert that authentication logic into this protocol state machine and to fix that logic problem with the protocol. So basically, any vulnerabilities that's at a network level, because we understand the protocol context, we can do something about it.
Is there an example where such has existed or?
Yeah. Yes, there is a vulnerability, I think it's in a university plug-in and play. So basically, it's a logical error in the protocol. And we can potentially insert a small state machine to deal with that vulnerability. Of course, for buffer overrun, even for buffer overrun, it's not necessarily that easy. It's not always easy to deal with, depending on where the buffer is overrun.
I mean, lots of people have worked on buffer overflow, and for most part, it's done at various levels and it's solved. I mean, if it's used, all those techniques are used, then it shouldn't be a problem. I mean, it's different.
Yeah, so there are different approaches, right? You can use software patching to fix to basically insert the check, the boundary check in the source code directly. But there's some problem with that approach. Even with StatGuard.
It is at the language level, it is at the OS level, at the hardware level. So, I mean, it's solved at various levels, and putting them all together, it should basically solve the problem.
No, it doesn't. The problem is it does not solve the problem.
Those are not used, that's why it's not solved. But
That's not true. That's not true. For example, for the non-executable stack, the return to libc problem can still evade that. So basically, there's basically various attacks to work around the mechanism like stack guard or non-executable heap or stack. It's true that when you have all those mechanisms in place, it can stop a lot of buffer overrun-based attacks. But it's basically arms race. There's always a new attacks circumventing those mechanisms. But here the key advantage of our approach here, we have a vulnerability-driven approach. No matter how you variate your attack vector, no matter how you variate your attack, we can protect you at a more fundamental level. Yeah.
My question is, if you have a vulnerability, will you be having only one kind of attack? I can use that vulnerability with different approaches, right? Maybe.
Yes, yes. You can have many different attacks against the same vulnerability.
So the thing is, then you will have only one state machine for one vulnerability?
Yes. There's only one state machine modeling it's really modeling the network operation aspect of that application. So basically, no matter how do you vary the attack, you can still exploit the same buffer. You may have different content. The payload, malicious payload, you can have various malicious payload to overrun that buffer. But no matter how you do that, we're checking,
This is true for buffer overflow.
No, I don't think it's specifically. I don't think this is specifically for buffer overrun. Basically, we provide a mechanism that we can show you what the protocol context is. Based on this protocol context, you can do whatever you need to do to protect your system. Sometimes it's a buffer overrun that you need to do. You basically do a boundary check at the network level. Sometimes it's a protocol logic problem that you need to insert, a partial state machine into the protocol state machine to basically correct the protocol logic problem at a different place. Yeah.
Couldn't there be two paths through your state machine to get to?
Yeah.
So wouldn't that be two protocols for the same vulnerability?
No, it's still this. It's still the. So if you look at this protocol state machine, if you look at this protocol state machine here, it's really there are many different paths that can lead to that vulnerable state. So by specifying that state machine, you captures all the possible paths that leads to that state, all the possible sequences of methods that lead to that state. Yes.
Just a question more. I mean, there was one word before that was the Outlook. I think it was, had the preview mode where people viewed it and the preview automatically viewed the attachment and it sent itself off. Would this be able to be used to do this, since that's kind of past the protocol?
I think for email, I don't think email viruses or email worms is really a big threat today. I think there's a easier solution than this to address the email worms and viruses. You don't do the preview pan, then you will not be so automatically exploited, and then you use antivirus software to scan the email content and to figure out whether you have a virus contained and cure the problem there. This is very good for I guess you can also apply this to email, but the problem is there are many ways for you to receive the email. Sometimes you can receive the email over web interface. So the problem there is really essentially that email that's going to be part of your file system causing the damages, rather than so for basically for all the file-based problems like viruses, the best solution is really the antivirus software.
So just to understand.
Yes.
Going back to your previous answer, actually,
Okay.
when you're talking about the email worms, actually the problem there I hear is that because the Outlook actually is configured automatically to open the attachments. So, I mean, if it is similarly, if you look at the code red, the problem came because XP actually automatically had this web server installed and people didn't know, right?
Right. So yeah, you can use Shield for that. So I think later on, that problem is fixed because by default you don't do the preview of your emails. But if that's misconfigured, you can still use Shield to trace on your SMTP protocol and possibly inspect the email content. It's possible to do that.
Okay, another question.
Sure.
You talk about actually the traffic being encrypted, right?
Yeah.
So, do you think there is any attack currently that actually uses encrypted traffic?
So basically, for end-to-end application-specific encryption, if we can get a private key in Shield, of course we can do something about it, and also it may not be inefficient to do that in Shield. However, it's probably not reasonable for Shield to obtain the private key for a particular application. In any case, for application-specific encrypted traffic, it's very hard to deal with. So I think there is always inherent tension between the security and privacy. The tension here is you want to encrypt your traffic to have your privacy. However, when you encrypt the traffic, it's not possible for third parties to inspect it. Another answer to this question is, for infrastructure-based end-to-end encrypted traffic, I believe we can address. Basically, we can say we can lift the shield at a layer of the for example, above SSL, so that shield will have the access to the encrypted payload and decrypted payload to inspect the traffic. Yes?
You had mentioned early on that there was one of the main problems with worms was that users just don't patch their systems. What kind of distribution network do you envision for Shield?
Right. So the kind of distribution we have in mind is to basically have like an antivirus-based kind of distribution model. This how antivirus works is that whenever there's a new virus discovered, the virus signature will be distributed to every end host. Or there's agent running on your system periodically polling for the new virus signatures. So this can be done similarly for Shield. Basically, we periodically distribute. Basically, whenever there's a new vulnerability, then there's a vulnerability signature authored. Then that vulnerability signature will be automatically distributed to everybody. At that point, you're protected. Yeah, so it is automatic in that sense because of the data-driven feature of the Shield system.
So to steal my question, right? Sorry. Any other questions? Okay, let's take a couple more.
Good. So I guess the goal is just to be outside of just Microsoft, right, in the future, to have like other vendors to also provide Shield things, or just Microsoft specific.
So this mechanism is good for everybody, really.
But it seems to require that vendors give up their protocol. Then, I mean, if people want to do this, they have to give up their protocol state table, which they made.
Yes,
Kind of
we're required to do that anyways, don't we? And yeah, third parties, they can, right, that's true. It may pose a problem in certain scenarios, other non-technical problems in some scenarios.
So, like in implementation, does it mean that when in the state machine it's executing in some function, essentially, then you are going to say that there may be an exploit. Like for example, v4, does it at a higher level does it really mean that if it's executing in some part of the code of the application?
Right. So all what we're doing here is basically we don't want to be so entangled with the application at the code level, at the executable level, or we want to be completely not in the process of the application. But rather, at the network level, we just want to passively observe the message that are passing by between the application from this host with some remote entity. And through this process, we figure out exactly, where you are in this protocol state machine. For sure that that application is executing some code, but we actually don't want to have that detailed knowledge. We want to be as separate from the application as possible. And that actually that's the reason why we have this edge of being easily deployable. Because we're at the network level, we're doing data-driven. We're just looking at the messages and to see which part of the message causes the problem.
Is it really at the network level? Because you are just, the Shield is executing the protocol layer that you showed, it was at the user level and it was just below the application between the socket layer and the... Yeah,
being at the network level meaning that I look at the network messages and being at a separate process. It's actually not really the So so our specific implementation is in the LSP. You can think of this as being part of a kernel, right? So being part of the network stack, whenever there is a send call that's being called, then there is a callback into the shield logic to do the deep inspection. That's exactly how some of the firewalls are implemented.
How to compare it with the host-based intrusion detection system, and how does it?
Host-based intrusion detection, there are many ways of doing that. Some ways is to use the system call sequence. And you can also do some sandboxing kind of schemes. It's essentially similar to some of those schemes. We're also intercepting, you can consider us intercepting the system calls.
Or just do whatever you do at the network level at the host level, like look at the packets.
That's what we do.
And
That's the mechanism how we carry this out.
Do we have time for more? Should we now? Well, let's. Well, we can talk to Dr. Wang offline, and I guess we need to vacate this room for the next class. So thanks. Let's thank Helen for the wonderful.
Thank you very much.